In this video, we're going to look at the quantum mechanical or the wave mechanical model of the atom. So one of the first concepts that led to the wave mechanical model of the atom was de Broglie's matter waves. And in 1923, Louis de Broglie proposed that matter, similar to light and other radiant energy, has both wave and particle characteristics. He derived an equation for the wavelength of a particle. So this is de Broglie's matter wave equation. So the wavelength of matter is Planck's constant divided by the mass of the particle multiplied by its velocity. Okay, and so this is the matter wave equation. So electrons can be compared to a standing wave. Since electrons have very small mass, their wave behavior is significant. So because mass is in the denominator and mass is very, very small for an electron, that makes the wavelength quite large. So it's appreciable. It's very noticeable. Now, in standing waves, we have things that are called nodes, and nodes are areas of destructive interference. Nodes are where a supercrest meets a supertrough. So a node will occur when you have a supercrest meets that's a supercrest, and a supertrough. They meet and they line up and they cancel each other out. That's destructive interference. There's also areas of antinodes, and that's where you have constructive interference. That's where you have a supercrest meets another supercrest, and they overlap and they double in amplitude. So when they overlap, they actually double like that. That's called an antinode, okay, or constructive interference. The same thing can happen with a supertrough. I just chose to use a supercrest there. Okay, so matter. So this is the important thing that you need to know. Electrons have nodes and antinodes because they are waves. We further have more evidence of electrons behaving as waves in this experiment as well. So we had light was regarded as having wave-particle duality, and waves are defined as a continuous traveling disturbance, whereas particles are defined as discrete bundles. Now, when we get to the subatomic level, the distinction between wave and particles seems to disappear. So at the subatomic level, the distinction between wave and particles tends to disappear. In the macroscopic world, so the large-scale world, only wave or particle behavior is evident, but at the subatomic level, both behaviors are detectable and significant. So probably the most famous experiment that showed this was true for electrons is the double slit experiment. And it proved that electrons behave as both waves and particles. When an electron passes through a single slit, you only have basically this one line right here where the electrons passed through, right? This proves that it's behaving as a particles because electrons that strike outside of the opening, so on these plates right here, they bounce off and they don't go through. So this has electrons behaving as a particle. They line up like this. Now, when electrons pass through a double slit, what ended up happening is you get this diffraction pattern. Okay? And it's essentially this pattern that we see, and that is only produced by waves. This diffraction pattern is only something that waves can produce. So when it's a single slit, we have this pattern. When it's a double slit, we have basically like a wave pattern. And these bright lines correspond to antinodes, right? So these bright lines right here are constructive interference, where you have strong electron striking, and these right here, like a strong electron presence there, and this is destructive interference. So no electrons are striking at this location. Heisenberg's uncertainty principle also contributed to the wave mechanical model of the atom. What Heisenberg said is that it is impossible to determine simultaneously the exact position and momentum of a single atomic particle. So essentially what we get from Heisenberg's uncertainty principle is that we cannot know the exact location of the electron. All we can tell is where the electron is likely to be. So as you can see, we are moving away from Bohr's model of the atom, where we have this electron circulating the nucleus like planets in a solar system. And now we're just basically talking about electrons as these waves of probability, where this electron is most likely to be. The next scientist was Schrödinger, and Schrödinger contributed to the wave mechanical model by producing a wave equation, which is a series of very complex calculations that will plot or give a three-dimensional probability plot of where an electron is most likely to be. So the wave equation requires an input of quantum numbers. So it looks at the quantum numbers, okay? And that produces a 3D probability plot of where the electron is likely to be. These areas of probability are called orbitals, and they have specific shapes that depend on quantum numbers. Now, this might seem pretty confusing right now, but we're going to stop and we'll look at what orbitals are in the next lesson. Essentially, they're just locations in space in the atom where you have a high probability of finding an electron. Now, you may have heard Schrödinger in the context of Schrödinger's cat. And this is essentially talks about the concept of superpositioning. All right. So Schrödinger's cat is a famous thought experiment. So this experiment never took place, right? And essentially what Schrödinger said is that let's pretend that you have a cat in a closed box. It's opaque, you can't see inside the box. You have this radioactive material, and you have a Geiger counter that measures the radioactive material. And this Geiger counter is connected to a pair of scissors and a hammer that can fall and break the vial of poison. Now, this radioactive material has a 50-50% chance of decaying. All right? So in the next instant, the radioactive material might not decay. And if it doesn't decay, it does not trigger the Geiger counter, and so the poison vial is not broken by the hammer. So if the material does not decay, the cat is alive. But if the material, in fact, does decay, then a particle will come out of the radioactive material. It will trigger the Geiger counter. The Geiger counter causes the scissors to close, snips the wire, the hammer falls on the vial of poison, and the poison kills the cat. So there's a 50-50% probability of realities. Either the cat is alive or the cat is dead. The concept of superpositioning says that if you are unable to observe either of these realities because the box is closed, then essentially we say that the cat is both alive and dead at the same time, and only the act of observing it will make one of the realities come true. So only when we open the box does one of the realities come true, and the other reality no longer ceases to be true. So this is the concept of superpositioning, that there are multiple states of reality, and the act of observing or measuring alters the reality. So let's fill in the blanks here. We have waves do not exist in just one location in space, but are simultaneously in many locations. In a similar manner, matter is not, or matter on the subatomic scale such as electrons, is not restricted to one particular location. Quantum particles, like electrons, may exist in many possible states. And so a state could be like a location. So a quantum particle, like an electron, can be in many places at the same time, each state interacting with each other. And when we say each state interacts with each other, some states do so constructively, and so there's a very high probability of them being in that location. And some states destructively interfere with each other, and there is a 0% probability of them being in that location. But there are multiple locations possible and coexisting for the electron. That is superpositioning. The act of measuring or observing a quantum particle causes all these interacting states to collapse into one state. And so we observe the quantum particle in just one particular place. So superposition is a property of quantum scale matter. Again, this is only happening, or we only really see this at the subatomic scale, which is the ability to assume many interacting states. Now, what I will say is, although I've indicated here that this is at the subatomic scale, in, I believe it was 2012, the Nobel Prize for Physics went to a group of physics researchers that allowed an atom, so not at the subatomic scale, at the atomic scale, to exist in multiple places at once. So research continues to go on in this modern level of physics. So when I talked about these orbitals, or these high probability locations of an electron existing, these came from Schrodinger's wave equation, okay? And so Schrodinger's wave equation allowed these shapes to represent the atomic orbitals in an atom where you are most likely to find an electron. And these shapes all sit on top of each other within an atom. Each of these shapes can only hold 2 electrons. So these shapes that you see here, this circle shape, these 2 lobes that are split apart, all of these shapes are produced by Schrodinger's wave equation, and these shapes show the areas of high probability of finding an electron. So let's actually write that in, right? These are regions in space of high probability of an electron existing. And that's the fundamental part of the wave mechanical model of the atom. We will look at the quantum numbers themselves and show how the quantum numbers lead to these different shapes in the next lesson. Thank you for watching.